Good afternoon, everyone. My name is Dev Soni, and today I am here with my friend Ridham Panchal. Together, we are going to try to explain you what is Floyd Warshall's algorithm and hopefully give you a little hint about its real life applications. So, before getting on to Floyd Warshall's algorithm, we need to know about some things first. So, let's get on with those prerequisites. Our first prerequisites, as you can see, is a weighted directed graph. Now, what is a graph? A graph, as you can see here, is a combination of nodes and edges. This here, right here, is a node. This right here is an edges. An edge basically connects one node to another node. Now, when the edge points from one particular node to another particular node, as you can see, there's an arrowhead right here. And when it contains some cost or value to it, then the edge can be described as a weighted directed edge. And the graph made up of such edges is a weighted directed graph. So let's get to the point. The cost of traveling from one node to another node is the total sum of the weights of the edges encountered in between them. What this point means, so let's say if you want to go from node S to node T through the path, the purple colored path here. So the cost of edge from S to B is 1 and the cost of the edge from B to T is 21. The total sum of this is 22, hence the cost of the path from S to T is 22. Similarly, if we take the red path here from S to D, the total cost will be 3 plus 5 plus 2, which equals to 10. Cycles. A cycle is just a closed path in a weighted directed graph. It means that if we start from one node and then following the edges, we should be able to get back through to that node. Suppose we start at 1, then we can see that we can travel from 1 to 2, 2 to 3, 3 to 0, and 0 to 1 back again, which brings us to 1. What are negative cycles? When traversing through a cycle, if the overall sum of the edge weights of the cycle is negative, then we term the cycle to be as a negative cycle. On the contrary part, if the overall sum of the edge weights of the cycle is positive, as you can see here, then the cycle is a positive cycle. So that's all for the prerequisites. Now let's get on to the formal definition of the Floyd Warshall algorithm. Now, what is Floyd Warshall algorithm used for? It is used to compute the shortest distance between pair of all nodes in a directed graph. That means if you have a graph such like this, then the shortest distance between A to D or A to E or let's say B to F will automatically be calculated through the Floyd Warshall algorithm. In mathematical terms, let's say there are n m nodes in a graph and n be the set of the nodes of a weighted directed graph. Then we have a function f which takes in three inputs k, comma I, comma j. This function defines or gives the output of the length of the shortest path from node I to j such that all intermediate nodes on the path, if there are present, belong to the set n1, n2 till nk. It just means that the nodes will be from 1 to k. Here the function f, I, and j can also be represented in a tabular form or rather a matrix of n by m dimensions. Suppose if you have a graph with 4 nodes, then f I k, I, j can be represented by a 4 by 4 matrix. Then to get on with each step, we have to follow this formula where f of k, I, j is minimum of f k minus 1, I, j or f k minus 1, I, k to k minus 1, k, j. This that means that in a further matrix of k, if you want to travel from node I to node j, then we will just see if it is possible to get a shorter path in traveling from node I to k and k to j, or it is short, or is it shorter to get a direct path from I to j. Then the final matrix Fm, I, j is the matrix which contains the shortest path between all pairs of nodes. Do not worry yet if you don't understand this mathematical definition. My friend here will explain you a theoretical example and hopefully everything will be clear.
So here we have taken a graph consisting four nodes denoted by A, B, C and D, and there are five edges. For mathematical purpose, we have to make a 4 cross 4 matrix as we have four nodes in our graph. If your graph consists x nodes, then we will have to make a x cross x matrix. So let me clear a thing first to you, that this side of the matrix denotes the starting node of the edge, and this side denotes the ending node of the edge. That means here, if a edge is going from A to C, we will its starting node will be A and ending node will be C. So we will take A from this side and C from this side and put the weight of that edge is to corresponding cell. Now let's start filling our matrix. First, edge is going from A to C contains weight minus 2. So we will put A to C minus 2. Now another edge is going from C to D. So we will put C to D as 2, weight of that edge. Edge is going from D to B. We will take D to B and put weight minus 1 here. Edge is going from B to A. We will put B to A as 4. B to C weight is 3. We will put B to C weight 3. Now you can see there are no edges going from one node to that node itself. So we will put 0 in this case, as you understand that from going one point to that point itself you don't have to do any work, or there will be no cost required. So we will put 0 in all such cases where ending node and starting node are same. So the diagonal element of the matrix will be 0 here, and the other cells will be infinite here. As you can see, there are no direct edges going from that particular node to another particular node. As you can see here, from A to B there is no direct edge going, so we will put infinite. Don't confuse yourself from this edge, as it is going from B to A. The direction matters here. So now we will try to apply our function here. This is our function which you have shown earlier. So here we will try to apply this on node A. So here we will try to go from one node to another node via node A. For that case, the rows and columns containing A doesn't make any sense to calculate it here again, as from going node A to node another node via node A doesn't make any sense. For diagonal elements, it also same. Now this is our function for node going B to C. So B to C was previously 3 here, and after that we are going B to C via A. So first we will go from B to A here, which is 4, and after that we will go from A to C here, which is minus 2. So effectively it will be 2 and it is lesser than 3. So the value get updated here as 2. From graph you also can see that going from B to C directly it is 3, but if you go from via A, effectively it will be 2. Same way we will apply that for B to D also. B to D previously was infinity, but first we will go from B to A here, which is 4. After that we will go from A to D, which is infinity. So infinity will remain as it is. After that we will check for C to B. So first we will go for C to A here, which is infinity, and after that we go from A to C, which is minus 2. So after that it will be effectively infinity here. So infinity will remain as it is here. Now we will go for C to D, which is previously was 2 here, and after going via A we are getting as infinity, so 2 will remain as it is here. For D to B, which was previously minus 2, but going via A we are getting as infinity, so minus 2 will remain as it is here. For D to C, previously it was infinity, and after going via A is also infinity, so infinity will remain as it is here. Now we have completed to check for going via node via A. Now we will try to check for node going via B. So for that we will do the same thing as I told you previously. Checking for rows and columns containing B and diagonal elements doesn't make any sense. So now we will apply algorithm for the rest of the cells. So first start with A to C. A to C was previously minus 2, but after that we'll go to A to C via B. So first we will go from A to B here, which is infinity, and B to C, which is 2. So effectively it will be infinity, which is not less than minus 2. So minus 2 will be remain as it is. Now we will go from A to D via B. A to D was previously infinity here, and if we go A to D via B, it will be also be infinity. So infinity will remain as it is here. We'll go C to A. Previously it was infinity, but we will go C to A via B. We will get infinity also. So infinity will remain as it is. For C to D, for C to D, Previously it was minus 2, but if we go C to D via B, we are getting infinity here. So minus 2 will remain as it is here. Now we'll check for D. D to A was infinity here. You can see here D to A was infinity here, but D to B is minus 1 and B to A is 4. So effectively it is 3. So D to A via B is 3, which is lesser than infinity. So 3 will be updated here. Now we'll check for D to C. D to C was previously infinity here, but if we go via B, we are getting as 1, as D to D to B D to B is minus 1 and B to C is 2. So effectively it's 1. So 1 is lesser than infinity. So 1 is updated here. So now we have applied our algorithm for node A and node B. Now we will do same for node C. We will go from one node to another via C and check if we are getting cost lesser than or not. So first we will go from A to B here. So A to B is infinity for in first case, but if we go from A to B via C, it is infinity. So infinity will remain as it is. We are going from A to D. A to D was previously infinity, but we'll go from A to C first, which is minus 2, and C to D, which is plus 2. So it is effectively 0, which is lesser than infinity. So A to D will be updated as 0 here. We'll do the same for B to A here. Previously it was 4, but after going via C, it is infinity. So 4 will remain as it is here. If we go from B to D, previously it was infinity, but if we go B to D via C, it is 4. As B to C is 2 and C to D is 2. So effectively it will be 4, which is lesser than infinity. So 4 will be updated here. For D to A, previously it was 3. And after applying our algorithm going via C, it is infinity. So C will remain as it is. Now D to B, which previously was minus 1. But after going via C, it will be infinity. So minus 1 will remain as it is. Now we will do the same thing for node D. We will go from one node to another via D. So first we will from A to B. Previously A to B was infinity, but we will go from A to B via D. So A to D is 0 and D to B is minus 1. So now we will do the same thing for node D. We will go from one node to another node via node D. So first A to B. A to B was previously infinity here, but we will go from A to B via D. So A to D is here 0 and D to B is minus 1. So effectively it will be minus 1, which is lesser than infinity. So minus 1 will get updated here. For A to C, which was previously minus 2, but if we go via D, we are getting it as plus 1, which is not lesser than minus 2. So minus 2 will remain as it is here. Now we will go from B to A here, which was previously 4. But if we go from B to A via D, we will get 7, which is not lesser than 4. So 4 will remain as it is. For B to C was previously 2. But if we go from B to C via D, we are getting as 5, which is not lesser than 2. So 2 will remain as it is here. Last, we will do for this for C to A. For C node, we are going from C to A. Previously it was infinity, but if we go from C to A via D, first we will go from C to D, which is 2. After that we will go from D to A, which is 3. So effectively it will be 5 and lesser than infinity, so 5 will be updated here. Now we will go from C to D. So C to B was previously infinity here, so we will go via D. So first we will go from C to D here, which is 2, and after that we will go from D to B, which is minus 1. So effectively will be 1, which is lesser than infinity. So 1 get updated here. So here you can see we have obtained our final matrix consisting the shortest path between all pairs of the node. You can check for going one node to another node via graph also. This all value denotes the shortest cost from going one node to another node. So this is how we can apply Floyd Warshall algorithm formula to our graph and matrix. I hope you have understand each and every point here. Still, if you have any doubt, you can rewind video and watch carefully.
Now, as I said, that Floyd Warshall's algorithm is a big part of the dynamic programming world, which means we have to learn how to implement it in a programming language. For our video purposes, we will be choosing the language C++. Right here is the snippet of our code for Floyd Warshall's algorithm. As you can see, there are two parts to this code. The first part is this one, and the second part is this one. This part right here deals with how to take the input of an n by n matrix. For a graph with n nodes, we will have an n by n matrix to store the input, that is the matrix F0. So right here we are just iterating through the loops. I is 0 and it goes till n. Then j is 0 and goes till n is for the columns. For each cell, we will take the input of a string variable. Then if we will check the string variable for its first character. If the first character encountered is I, then it means that the input is infinity. Then we will just assign the value of the cell as int max. If the first character of the string is a dash or a minus, then we will convert the string into an integer form and multiply it by -1 at the end. In if none of these cases are there, that means it's just an ordinary number. So we'll have to convert the string into the integer form directly and store the value in the cell as it is. For the part of the Floyd Warshall's algorithm, we can see it's a very simple implementation. There are three consecutive for loops and an if condition. The first for loop, k equal to 0 and k is less than n, indicates the matrix F0, Fa, Fb, Fc, and Ft, and so on. So for an n graph, we will run this first loop n times. Then the next two are just iterating through the matrix. This the I is for the rows and the j is for the columns. For each cell, we will check the condition that if the path from the node I to k and the path from the node k to j, if the sum of these is less than the direct path from node I to node j, then and if none of these values are int max, that means if none of these values are infinity, then we will just update the value. So let's say if I want to go from I to j and we are designing the matrix for fb. So in matrix fa, if the value of I to j was greater than the value of I to b, then b to j, then we will just update the value of the cell I comma j. So that's it for the code. Let's get on to the complexities of this code. So first we come to time complexity. As we can see, there were three consecutive for loops in our code, and each one has to iterate n times. Thus, our time complexity will be big O of n cube. Space complexity, as we can see, we have to assign a 2D array for storing the input matrix. Therefore, our space or the auxiliary space we require is big O of n square. Let's get on to the advantages and disadvantages of Floyd Warshall's algorithm. So, let's come to the advantages. The Floyd Warshall algorithm. It is suited for both positive and negative cycles of a weighted directed graph. As you can see in the theoretical example, we took some edge weights as negative numbers as well as some positive numbers. So the sign is not an issue here. Secondly, the algorithm has a very simple implementation. As we can see in the code, it is just a series of for loops and simple input of strings. Thus, the implementation is very simple and not anything too complex. Thirdly, or lastly, the algorithm is independent of the number of nodes and edges. The user can always choose as many nodes and as many edges he wants. Cons, as we can see from the code, there are three consecutive for loops. So the runtime or the time complexity of the code is cubic, and we have to assign a 2D matrix extra for storing the input matrix. So the quadratic space complexity is also there. It just makes the execution slow and requires more memory in the heap. The second con is it only stores the minimum distance between a pair of nodes and knows the actual path should be taken. That means in the final matrix, we will get the shortest distance between any two nodes, but we will not know which path to take. So these were the advantages and disadvantages of Floyd Warshall algorithm.
Now let's come to real life applications of Floyd Warshall algorithm. As you know, Floyd Warshall algorithm is very useful in our regular life. Here we have shown you some examples of Floyd Warshall algorithm. There can be many more also. Google Maps. To compute the quickest path from one location to another, Floyd Warshall algorithm is used. Here, points can be used as node and the path can be used as edges. Social network analysis. To connect people with their mutual interest, we can use Floyd Warshall algorithm. Here, people will be used as nodes and their interest, hobbies, or other things can be used as weights of the edges. Flight path. Let me explain you this example in detail. Assume there is a person named Ramesh is living in Kochi and he wants to go to Leh, but there is no direct flight from Kochi to Leh. He needs to go via other cities as Bombay, Delhi, Srinagar, or Leh. So here are some possible paths he can go from Kochi to Leh. Here there can be two parameters. If Ramesh wants to take the cheapest possible flight or the shortest possible flight. So here we will take the cities as our nodes and the flight paths as our edges and the parameter as our weights of the edges. So first let's take the cheapest path. Ramesh wants to go from Kochi to Leh for cheapest flight. So here we have taken the data from online that these are the prices of the flights from one city to another city. We have created this matrix here. As I have teach you earlier, you can create this matrix and solve for Floyd Warshall algorithm. You will get the shortest flight from Kochi to Leh here in terms of flight cost. So here we are getting the least cost as 57,426. You can calculate it by yourself. After that, if Ramesh wants to go from Kochi to Leh by shortest path, it means Ramesh want to reach earliest as possible. So here we have taken the kilometers distance here and created our matrix here. And we will apply Floyd Warshall algorithm in this and we will get the shortest distance via this city is 2,947 kilometers. You can verify this result by applying Floyd Warshall algorithm by yourself. So this way, Ramesh can reach from Kochi to Leh. Here, here are some factors we can take as parameters as our edges weights. We can take time also. We can take distance also. Or it can be fuel combustion or CO2 emissions also. So this is all Floyd Warshall algorithm is for. We would like to thank our Professor Manish K Gupta and Professor Manoj Raut for giving us a unique opportunity to work on this project. For research purpose of this project, we have explored many domains like machine learning, cryptography, and etc. We got to know that discrete maths is very useful in these domains. We have explored Enigma machines, Alexa model, and QR codes for this project purpose. Thank you for providing us this opportunity to explore these domains. Here, this is our team members.
Our group has made this little website on Floyd Warshall's algorithm as part of our project. This website is a minimal website with several options. In the introduction tab, you can read a bit about Robert Floyd and Stephen Warshall, the creators of this algorithm. In the algorithm tab, you can learn about the algorithm itself. Here, you can input values in a 5 by 5 matrix, which is similar to the graph with 5 nodes. Let's say if you want to enter any random values and see how it runs. I've already entered some values which I'm going to show you here. Upon clicking the submit button, we get a final output graph like this. Notice the values of 1 lakh here, they just demonstrate infinity. Other than that, these are the values. So thank you for watching. We highly appreciate your patience to sit throughout this video. If you have any doubts, feel free to ask them in the comments. We'll try to reply as soon as possible. Thank you.